Okay, so let me say a couple words about the next homework. Right. So the first problem, I think this is kind of a cool problem. Show that if f is an extension of k, and u and f is algebraic over k of odd degree, then ku squared is equal to ku. So that is the smallest field that contains ku squared. It's exactly the same as the smallest field that contains k and u. The odd degree, of course, is very important. Notice that you always get this containment. All right. What can you say about the relation between ku and ku squared if u is transcendental? Number two is actually kind of important. There's a number of important things in this about that apply to finite fields. Let's suppose that f is any field at first, and G is subgroup of the multiplicative group of the field. So, of course, take out the zero element of the field, and what you have is a multiplicative group. Let G be a subgroup of the multiplicative group. Show that if G actually is finite, then G is cyclic. Right? This is actually a very important thing about fields. So if you have any subgroup of the multiplicative group of the field, it's finite, it has to be cyclic. That's kind of cool. And the proof, let me give you the hint on this. Think about the characterization of finite field, the classification of finite field universe. That might help. Number B, show that if f is finite, so if the field is finite, the product of any two non-squares in f is the square of f. This is kind of weird, right? Because let me give you two non-squares in rational numbers, 2 and 3. Neither one of these are square, right? Because there's no square root of 2 or no square root of 3 in rational numbers. 2 times 3 is 6, which is also not a square in the rational numbers. But in finite fields, if you multiply two things that are not squares, you get a square, which is kind of cool. And this one's fun too. If the field is finite, every element of the field can be written as the sum of two squares, right? Again, this is wildly untrue for lots of fields. For example, take the rationals, take the real numbers. No negative number is the sum of two squares ever, right? But in a finite field, every element is the sum of two squares. Number 3, suppose that f and k are fields with f algebraic over k. Now, suppose you can squeeze a ring R, an integral domain, between those two fields. Then R has to be a field as well. That's kind of cool as well. So if you have two fields and the big one is algebraic over the small one, then any integral domain you stick between there also has to be a field. Number 4, let K be a field and let U and V be elements of some field extension of K, and they're both algebraic over K. Show if the degrees of U and V, the degree is of the algebraic element is the degree of its minimum polynomial. So the minimal polynomial of U has is a degree m, and the minimal polynomial of V is degree n. Then K adjoined with U and V over K is less than or equal to mn. And if the GCD of mn is 1, then you have equality. By the way, that last bit is not an if and only if. And finally, 5 is kind of neat. Find all of the automorphisms of real numbers that fix Q, right? I almost feel like a baby analyst. I do this part, right? So you might have to use something similar to continuity. Like that. Okay, any questions? All right. Okay. Oh, let's see what on this situation. Okay, any questions from last time? Questions? Titles over here. All right. Okay, so the last time we were talking about algebraic elements and extensions, and we got some nice characterizations. In particular, if an element U is algebraic, then it's actually if U is algebraic of K, then K adjoined with U is really K adjoined with X modulo the ideal generated by the minimal polynomial. And the last example I gave you was we looked at there's five of these things in complex numbers, right? One of them's real, and there's two pairs of complex conjugates. We remarked that this polynomial is two Eisenstein, so it's irreducible. QU, all five of these fields are isomorphic to this, right? So, well, theorem, this is a theorem about field homomorphisms, which are always monomorphisms. Theorem 819. Let tornado from K to L be an isomorphism fields. This just means it's onto, because remember, any homomorphism that's not the zero homomorphism, which I will never assume here, is 1-1. You an element of some extension K and B an element of some extension of L. Then I can extend this homomorphism to an isomorphism KU isomorphism LB. So the isomorphism that I started with can be extended to an isomorphism from KU to LB. This homomorphism takes you to B. If and only if one of the following holds. There's one earlier case that you might pick out pretty quickly. Can anybody think of the condition where just this field isomorphism can be extended to this by taking U to V. Well, how about if U is transcendental over K and D is transcendental over L. So if they're both transcendental over their respective fields, then I can do it then. Now I guess the second case needs to deal with U being not transcendental, so algebraic, right? So in this case, I will say U is a root irreducible f of x and kx. And what? You're supposed to condition is that this just means that U is algebraic, right?
We want kind of a, I guess, corresponding like polynomial in L of X.
Yeah. Corresponding polynomial, I'm going to call this. Is roots corresponding, and let me clarify what this means. So the corresponding polynomial just means what that field isomorphism does to the coefficients. By the way, I did use the adjective irreducible here, and I didn't say anything about it on the other side. Right. Do I need to? Try to prove this fact. If f of x is irreducible and tornado is isomorphism, then the image of f of x also has to be irreducible. So irreducible here, and this being an isomorphism means irreducible. Note, I'm going to note first that I'm going to call this star. Given the same thing I did up here. Is a deal. So what do? I just take the rational function here. These are polynomials in Kx, and I turn them to corresponding polynomials in Lx. All right. This is essentially, this isn't exactly polynomial evaluation, it's just changing. It's easy to verify that because the original one here is an isomorphism, then so is this, right? You don't have to prove 1 to 1. And of course, X is transcendental here, so, and it's pretty clear this is on two, isn't it, right? Because certainly every element of LX is in this, and so since this is a field, after you've got every element of L squared back at X, you've got explosion. Everybody okay so far? So in the first case, so for example, if U is transcendental, over K and B is transcendental over L. So if these hold, then and the composite homomorphism is what's desired, right? Because we already know that KU is isomorphic to KX because the fact U is transcendental. LX is isomorphic to LU because it's transcendental. This is the composite takes U to X to, and sorry, that should be A to B. Right. Now, on the other hand, if two holds, that is, if U is algebraic over K with minimal polynomial F, it's called, isn't it? Yes. Then I get KU is isomorphic KX modulo F of X. Is going to be started with that. This is remember this tornado star takes KX to LX, but it also takes F of X to this, and so it induces this isomorphism. Right, by the first isomorphism theorem. And if you follow the path, U corresponds to X. We saw them prove the algebraic. X goes to X, and then X goes to B. I will leave the other direction to y'all as an exercise. It's not difficult. Let me bring this example up. So, this is so much good example before, but I'm going to warm up on this. I'm going to go much more in depth in this example later. Let alpha be the real cube root of 2, but omega equal -1, right, will make it 3 root 2, which is the primitive cube root of 1. This is the primitive cube root of 1. it's a minimal polynomial, it's that. The fields. This is real. And here, omega bar is the complex conjugate of this. Are all isomorphic. They're all isomorphic, they're all distinct. And the easiest way to see this is this one. This is a subfield of reals. And these two aren't. What happens when I intersect these fields? Actually, I'll need them so too. What is this field? Certainly this contains Q. Q is in all three of these. But how do I know that there ain't something else there? Let's call this F. F contains Q, agreed? What's something that contains F? I can do better than that, right? Everybody agree with that? Here's Q alpha. Q. What should be the degree of the minimal polynomial of alpha, which is 3. And last I checked, what does this mean? This is a prime example of how it's there.
It means that either the degree of Q alpha over F is 1, or the degree of F over Q is 1.
So I'll do it from this perspective. This is either 1 or 3, which was like ready. Tell me why it can't be 1. What happens if it's 1? That would mean that F which would mean in particular, well, actually, our question is in Q alpha negative, right? But anyway, it would mean in particular that this thing has to contain Q alpha, right? Right, this intersection would be all of Q alpha then Q alpha omega has to contain Q alpha. What's the degree of Q alpha omega? These three fields are all isomorphic. So if this was degree 3, the other two have to be 2. And in fact, the minimal polynomial, these are the other two roots, right? This thing doesn't contain Q alpha. In fact, alpha is not in here at all. So this can't be 3. Right? Because if this is contained in here and this is a degree 3, then these two have to be equal, right? But Q alpha doesn't have any non-reals in it, and Q alpha omega does. So that's off the table. So in particular, that's 3. No choice, which forces this to be 1. Yeah. Okay. Any questions? All right, the next theorem basically says that if I have a field and I have any polynomial, I can find a field where that polynomial has a root, which is really, that's an important thing. This is why algebra is more believable than analysis, right? Well, I'll tell you that at the end of this. Let K be a field and F and Kx a polynomial. Polynomial 3. And so I'm implicitly assuming that this polynomial is of the 0 polynomial. And there's a simple extension of K. Okay. Such as polynomials. 1. There exists U and F such that FU is 0. And B, the degree of KU over K, the degree of KU over K is less than or N. And equality falls. Anybody want to guess on the condition on F makes equality hold? If and only if. F makes it irreducible. Fans. And finally, if F is irreducible under that condition, this is irreducible in K of X, then KU is unique up to K of isomorphism. And in this case, we call K adjoining with U as the field obtained by adjoining the root of K. Okay. So here's the situation. You got some field, you got any polynomial degree in. There's a simple extension such that there's a root u in f, such that the polynomial, the original polynomial has a root. The degree of the extension is less than or equal to the degree of the polynomial. Inequality holds if and only if f of x is irreducible. And finally, if f of x is irreducible, then ku is unique up to k isomorphism. And in that case, we call k of u the field obtained by adjoining a root of f to u. So, what do you suppose the importance of the polynomial being irreducible is? I think I'll probably start with an example. So let me give you. Let's let k equal q. Right, and let f of x be x4 minus x squared. Now, what happens when you adjoin a root of this polynomial to q? Well, it's not clear, and I'll tell you why. This polynomial is not irreducible. What are the roots of this polynomial? You got four roots to pick from. Two of them are real and two of them are not real. Right? So what do I mean when I say I join a root of this polynomial to the field Q? You've got to give me the follow-up question about which root do you want, because you're going to get different results. Q adjoined with I, if you pick I, is going to be not a subset of the real numbers. And Q adjoined with square root 2 is going to be a real field. And these are not isomorphic fields. Because in particular, one of the fields has something that squares to -1, and the other one doesn't. So they can't be isomorphic. That's the importance of irreducibility here. So let's prove this formally. Any questions? Let us take we'll take this polynomial and factor it with its factors in k of x. And I'm going to call these irreducible. Think of these as prime factorization, if you will, of x. And of course, the degree is greater than one. Now, consider. I'm going to take P1 for the first part of this. As we've seen before, this is a field. Because KX is a PID, and so P1X is maximum. Because it's polynomial degree of at least one, and a non-zero prime is maximal in PID. Now, consider consider this map here, which takes the element K, the element K plus P1X is 1 to 1. So K is a subfield. Or construed as a subfield, KX mod. The image of K is a subfield, which is probably more correct to say. Now, I need you to be a root of f of x. So consider this. From the polynomial ring kx into kx equals how does this work? This works just the way I think that you would think it works. This takes to and notice that. So this is just a projection from kx onto this field where you take g of x and you go to its coset. Now, notice that, of course, I P1 of x, P1 of x, it's the ideal P1 of x, which is 0. So in particular, P1 of x is in the kernel of this map. Note now, I'm going to find u to be pi of x. This element is found kx. And notice that P1 that P1 of u is equal to 0. So. U is. One X. In F. So. U is. Because P1 is advised, P1 of X is advisory of X. You remember we factored F of X getting into the product of primes. Right. So this establishes this. My U is the image of X and works out the way it wants to do. The degree of KU over K is equal to, remember KU is just this. Which is the degree of P1 X, which is less than or equal to the degree of F. So that establishes it. That this is less than or equal. And if equality holds, right? Because remember, F of X is the product of all those PIs. And so if the degree of these two are the same, then F of X equals P1 of X, and so it's irreducible. And if F is irreducible, then equality holds. Because if F is irreducible, then my factorization is just F equals P1. And that means that P1 and F have the same degree, and you get equality. And I think we can kind of talk over the three a little bit. All right. Any questions? Okay. Here is kind of a really nifty result on small extensions. And hopefully you'll see what I mean. So if an extension F over K is small, then it's algebraic. More to the point. Let us suppose that F is finite. So F of K plus N. Then F is finitely generated in algebraic. By the way, before we prove this theorem, I think it's worth noticing a couple of things. This isn't, this condition is sufficient for algebraic, but it's not necessary. So for example, it turns out that U F is algebraic. Now, let me ask you, this, there are a couple of things about my statement that probably aren't obvious or. First of all, this is the smallest field. So if you go back to like our earlier definition of fields, how do you get this field? Well, I'll take this as a subfield to say the complex numbers. You could actually even take a subset of the real numbers. And my set X might be the square root of all the primes, right? This is a countable set. It's a subset of the, real numbers. So technically, what is this? This is the intersection of all subfields, say the real numbers, that contain Q, that's all of them, but also contain the square root of every prime. Notice this can't be all the reals self, right? Because the reals don't count. This never be IE. But is it clear that this is algebraic over Q? Maybe not. You need a couple of things, right? You need that the sum and the product of two algebraic numbers is algebraic. Now, just for fun, this is what an algebraic number time. I cube this and multiply by 86 and subtract 1, and then I square that, and then subtract, and then take the power of that, subtract 2 and 0, right? So there's probably some algorithm that builds a polynomial. Alpha is x plus 2x plus x plus 2x plus 6. It's a little bit harder to discern if this is algebraic, but it is. Now add these two. I'll give you buffalo nickel if you tell me what a polynomial is. I've got no idea. Right? But this number actually is algebraic. Right? It's composed of roots, of sums, of things. And we've also got this little algebraic number here. It's the root of this polynomial. But how do I know that this thing divided by this is still algebraic? It's not clear at all, is it? I mean, it seems to be. But of course, the definition of algebraic is algebraic of the cube is it needs to be the root of some polynomial. Put your money where your mouth is. All right. It's not clear at all. By the same token, it's not clear that if I get some big, huge mess of these things up here, it's going to be algebraic. But it is. Right? This is actually algebraic over here. It also may not be clear that it's not finite dimensional, but it isn't. You can actually show that all the radical p's form a linear in set of Q. Right? So the takeaway from this is if you have a finite degree of tension, and we're going to be looking a lot at that for applications, then not only is it finitely generated over K, but it's algebraic over K as well. And we're going to use that to do some of that stuff. Okay, any questions? I think that's good for today. The math club, you might be interested in this week. Hazel Torek is going to be talking about William, which some of you might be interested. This I think would be even more focused on William the other one. So I would I'd pay attention. If you got the time, come see that. Other than that, y'all have a good weekend, and we'll see you.